Thank you so much. It's nice to be back after 7 years. I had to look it up. Since then, I changed jobs. I actually managed to work in geospatial data now, finally, for the last few years. Very exciting. At TileDB. And I'm just going to talk about what we're trying to do with geospatial data, show you a bit of code examples, and just pretty much play around. And there's going to be a lot of visualizations, because I just really enjoy showing them. Geospatial data, the goal is what we want to do is we want to put all geospatial data in one single database, which is kind of easy when you have tables and just lots of rows and columns and that kind of data. But if you have geospatial data, you have loads of differences. We have different projections. You need to keep track of that. There's not just only points and lines and polygons, but there's rasters in many different, obviously, dimensions. You can make them 3D, 4D, how big you want, whatever dimension you want to add to it. And then also, there's a lot of data formats. I'll show you that in the next slide. But mainly, I think this is just the best comic ever about the complications of geospatial data. You can just use it to your advantage. Change your projection, and you can just escape. This is kind of my attempt to summarize geospatial data. I know I've missed a lot of data formats. There's way, way more. But this is kind of what we've been focusing on. So we want to have rasters, multi-dimensional rasters, which kind of means add different bands if you look at satellite data, or add a time component, make it 4-dimensional, 5-dimensional. Also geometries and point clouds. As you can see, they're all in different data formats. I had a bit of a debate with my colleague Sean about this. What do we put in? Do we call it really legacy formats and cloud formats? What do we do here? And what are the tools to really mention? This is what we came up with. So we do have legacy formats, which are kind of what I could define as the ones that you could use locally on your own machine still. And what happens if you have just way more data? That's kind of what we decided to call that cloud formats, like the COGS, ZAR, GeoPython, for point clouds, the EPT, for instance, and then the open source tools you might want to use for each of them. You see a few coming back here, the GDAL. I don't know why we didn't put it for geometries as well, because it does that as well. And then Shapely, Fiona, and GeoPandas as well, of course, coming back here. And then for point cloud, the PDAL mainly. And we can talk about how to pronounce all these later as well. What we're kind of trying to do is make this work with TileDB as well. So not change much of the tooling, because, well, a lot of people, once you finally know GDAL, which I've been working on the last 2 years, and kind of getting it now, you don't really want to change that anymore. You want to keep using it, for instance, but you do want to make it a little simpler. And also maybe use geometry data together with your point clouds and all that. So that's kind of where I'm trying to show you how you could just combine everything with everything. And just a few little examples really only, because we've just been now to the point where we can read all the data, ingest all the data, visualize it all, even combine it all together in one visualization, which I leave to the end. And all the code is available in Jupyter Notebooks. Sorry about the difficult link. And I'll show it again in the last slide. Especially, I did this because I'm pretty sure that in my slides, I've forgotten a lot of the imports of the packages, because then it would become a little unreadable. So if you go here, this is on TileDB Cloud. Don't need an account. You can just go to this site. There's 3 notebooks there. This is an example. And at the top right, there's a little download button, so you can just download it from there directly. Let's just start with a point cloud, because why not? And how would you get that into TileDB? Because I decided to just show you and then explain what you actually get. You can use PDAL for this. Create a PDAL pipeline, and I just read a las file, the outson.las, which is like the example, I think, that's always used by PDAL. I create a pipeline. And the only thing I have to add here is that I want to write to TileDB array. And I'm calling this name, this array outson. And in this case, it will just write it directly to my local directory, wherever my notebook is at the moment. And then I can just define a lot of different options here. This doesn't really matter for such a small data set, but if it becomes a really, really large point cloud of billions of data, you kind of want to set this right, the size of the tiles and how it's all partitioned. And then I just execute it. This takes about a minute to run. Obviously, it depends a bit on your computer. Same for raster data. Just, I'm using GDAL in this case. I have three TIFF files, with three bands, the red, green, and the blue. As with GDAL, I have to build a VRT file first to combine them together. Then I say, I want to write this to a TileDB array. And the trick here is, again, I just have to say, write it to TileDB array instead of like whatever other file you want, format you want. You're able to do this. And then I can just play around a little bit with the settings as well. And that's done. I have an array. It's written. This is really quick. It takes like a few seconds to write because it's not a lot of that much data. Same. I can use import a shapefile as well. I just say, this is my shapefile. In this case, these are just a small set of buildings from a larger New Zealand buildings dataset, which is a great open source dataset. So I have a shapefile. I'm telling it just to write me an array. And I use OGR to OGR to that. And I say, OK, write it to a TileDB array. And that's it, done. So now I've got data. Now I can actually show you what it will look like and how to do this. So I got my data. I import the TileDB package in this case. And when you're working with arrays, the schema is really important because it tells you what your data actually looks like, what dimensions are, where they are, and what attributes are there together. And I switched my slides around just a second before my talk. So let's show you first what a schema actually is and what the data model of an array is like. As you can see, the rasters and the point clouds and the geometries, they're kind of in two categories. So a raster data is dense, because for every pixel, let's say, in your data set, you have a value. So for my two dimensions in this case, the D1 and the D2, I have a value for everything. And then on top of that, and the dimensions are important because once you want to load your data back in, that's where you slice your data on. It goes really quick. And if you have any other attributes also included to your data, you add them to the attributes because that's the ones you're probably never going to select your data on. So to keep it really fast, you want to keep your number of dimensions the lowest. So that's the domain, my dimensions. In this case, it's only 2, but I can have many more, of course. So if I would have satellite data, let's say Sentinel-2, I have the X and the Y, but I also have loads of different bands. And I'm pretty sure we'll probably want to load my data or slice my data based on these bands. So I'll add them in as a dimension as well. And I'll do the same for time. If I want to look over time, I add time as a dimension in as well. And then point clouds and geometry, they're slightly different because they don't have a value for every single pixel if you would have a regular grid. So in this case, it's stored slightly different. I'm not going to go into details here, but the idea is here that it's fine to have a lot of empty space. So you only, of course, write the data where you actually have data. In this case, I have 2 dimensions again and a lot of empty cells. But the rest pretty much stays the same. So I have the dimensions, the attributes, which in this case I probably have a lot more like in the buildings case. I have, I don't know, the color of the roof, what kind of building it is, the address, whatnot, hanging on to that. And for point clouds, there's also loads of attributes like the intensity, the RGB values, and all that kind of thing. You wouldn't really want to put that in your dimensions because you're never going to really slice your data on that. And then for both, there's as much array metadata as you want that you can add to it. For instance, when you load your data with GDAL, it automatically just adds everything that GDAL knows about your data straight into that. So when you print it out, I'm sorry, there's a lot of numbers here. I just want to focus on the array schema. The domain, as I mentioned before, for a point cloud, I have the X, Y, and Z only. And then I have the attributes below that, so the intensity and RGB and everything else. And what I really wanted to point out, yes, this is automatically written as a sparse array, because it says sparse is true. And also the one below that, I can have duplicates, in this case, in a sparse array. So you can have same location, multiple values, just maybe over time things have changed, things like that. That is quite a useful feature you might be able to use. Array schema for a raster, pretty similar. We have a domain again, and in this case we have the X and the Y in the bands. And this is just GDAL, outputs that automatically for me. And the attributes are the TileDB values, that's what we call it. And in this case, sparse is false. And again, if you want to create a more complicated raster, which is really easy, you can do this differently. You just read all your data with raster.io and just write it directly with the TileDB Python API into the right location. So I can have bands, X and Y, and also time, for instance. I'll show an example of that in a second. Let's query some data, because we have data now, kind of know what it looks like inside the array. Now I import the TileDB package again, and I open the file, the array. So I just say TileDB open as an array. I'm just going to slice a little area from this, in this case, Sentinel-2 data. And do some stuff, pretty much load the data, transpose it around to make it to the north, go up north. And this is all using just a NumPy package. And then I have to kind of, because I have 3 bands, the red, green, and blue, I want to normalize them between 0 and 1 and plot them all together. And I know I've gotten some imports here. They will be in the Jupyter notebooks. So that's pretty easy. Load the data and just use NumPy and everything else. You can do the same with the multidimensional raster data, as I said. And I'm not entirely sure it's super visible, but in this case, the array is a little larger. So I have, again, the bands as a dimension. So the band, the X and the Y, but there's another one there at the end, that's time. So now I just load all that data in and just plot it out, the change over time, pretty much from one single array. So at the top, you can kind of see it get drier over time, last year in the Netherlands, and in RGB at the top, and also NDVI, just a combination of the different bands of the red and the near infrared. So once your data's in, you can just pretty much use it as before, but I'll get to that in a second. It loads really, really fast. Point clouds, let's play around with that back again. Open the array again, and why not put a point cloud in a pandas data frame? Don't recommend that for really large point clouds, but it is really nice to play around with a point cloud you don't know yet. Try to understand what's actually in it, look at a small section, maybe change the classification a little bit, add attributes or columns to the data, and just try to color it and show it differently. So I can do all this really. I can just load it all in the pandas data frame, just use the 2 dots between the brackets. Probably don't want to do that, as I said, or just load a smaller region, so the X, the Y, and the Z again, and then I just want all heights, of course, or I can then also query on different attributes, because I don't need them all, not interested in them, so only intensity or classification, or only maybe the intensity between 10 and 100, for instance. So you can almost just play around with the point cloud data in this way, using pandas. And here's how the next step that we worked on. How do you visualize your point cloud? And how do you do that especially in a Jupyter notebook? We've built this ourselves. This is based on the Babylon JS gaming engine, which is open source. And it's really cool. I loved working on this. I learned a lot of TypeScript myself while doing this. Basically, you load your data into a gaming engine, and you have to set the cameras as a gaming engine works, the lighting, and you have to play around. You can really move around your data quite in a fun way. So this is how we did that. That was a TileDB. I'll have the links to the open source projects in a second. You load the data, build this in TypeScript, wrap it up in a Jupyter widget, I think they're called, and then we build another Python package around that to be able to load that into a Jupyter notebook. And in this case, I just query a little bit of my data. I think this was about 1.6 million points in the end. Have to convert it just to be able to play around with this into a dictionary, and then show my point cloud and I can just set the point size, the width, height of the frame and everything. So this just shows up inside your Jupyter notebook, and it worked. So this kind of makes it really interactive. I've loaded my points from the array into a dictionary, and I can play around with it. Zoom around and in and out. And as you noted, it does not load all the points immediately. It really is kind of clever looking at where you're actually looking at. Only these points will be loaded in. Let's do some geometry data, because of course we want to be able to load that in a GeoPython data frame, and we can. And this was really cool to play around with, because just got my buildings array, tried this. I wasn't even sure if it would work, and it did, because of all the cleverness in the background in GDAL, Fiona, and all these other packages working together in the background to make this work, because there was a TileDB connection between all these. This works as well. And again, I added Pio, GRO, and Arrow both as well, because we also figured out if you add these, it becomes really, really fast. Doesn't really matter for these small amounts of data, but if you want to read a lot of data, it got really fast. And I think we did some benchmarks against different formats, and I'm pretty sure we were loading data faster than GeoPython. So I just got my buildings array loaded into the GeoPython data frame, and can play around with that. And now I know I don't have to use buffer anymore, so next time I'll do this a talk like this, I will use the new updated way of doing this. So I just created a buffer of pretty much a circle, and I wanted to just read the buildings within that circle. And this is kind of where the most work went in, to add, of course, a spatial index to TileDB arrays, because there wasn't one. So that's been added. So we have a TileDB index, and that pretty much is the center of each building at the moment. So it just goes and find all the buildings that have a center within the circle. But there is some extra cleverness around it, with some extra bands to make up for the buildings on the side. There's a blog about it if you're more interested on how that actually works. But that makes it just possible to load your buffer or use a mask on your TileDB arrays with geometries. Now the cool one is actually to use that geometry data that is in a TileDB array with a point cloud. So I was interested in this building. I think because it was a school, so I load this out, load the geometry of the single building from the array, and the next thing I have to do is use this, turn this into a a geometry, to be able to find the points within that building. And I can use GeoPandas for that one. And as you can see, I have here all the points that are within that building. So 2 different arrays, point clouds and a geometry. They can work together in this case. And that's the building on the left. And again, I loaded the data, And there was some classification in this data, but no RGB values. So because it was all in a GeoPandas data frame, I could just play around with it and color the different classes, so the buildings, the vegetation, and the ground surface. So it's really quite fun way to play around with two different data sets together. And now and also see the misclassifications, because the geometry said, no, this is all a building on the top left, but no, there were actually some trees in there and a point cloud. I want to just show a little bit more about how TileDB really works, because these are all small examples. You can run them locally, but it becomes really good when you have a really large amount of data. All the code will work exactly the same as I showed before. Your data, though, doesn't have to be local. It could be anywhere. It could be in any of the cloud providers. The one I use all the time is S3. So I write my array directly to S3. Instead of having my local path, I just say S3, whatever, to my key and bucket. And then I can load it in a similar way. So that's kind of the core of TileDB. It's the open source project where all the reads and writes happen. It's cloud optimized. And yeah, there's way more in there I haven't even talked about yet. And then around this, we have the TileDB Cloud platform, where you can have a lot more more scalable features, where you run task graphs, do everything in parallel automatically, really easily, and then there's loads of APIs, and which are then again, of course, all open source again. So it's not only Python, there's also R, Javas, all the C versions, JavaScript, Go. We also do a lot of machine learning and data science, so there's also links with Keras and TensorFlow and all that. And then also very domain-specific applications. So you can see there's GDAL and PDAL there, that of course I've been talking about, but we do a lot of in the life sciences and genomics as well, which is all the other ones that you might not have heard of. How does it work, the processing? We don't use tasks, we developed our own. So if you just want to do loads of different data things, you build a task graph, that's the idea. And every process just gets scaled out to different service. It just spins up new images for you. This is an example of what I did. Just ingest the geometries with a task graph. This is the whole, I can't remember the name, but that new open source buildings data set, which has 700 million, almost a billion buildings in it. And it took me 20 minutes to do that. It doesn't cost a lot. And it's quite automatic. You just say, just chunk it up and do it all in one go for me. This would take forever if I would do this locally. Done the same with the 500 million point clouds, because I wanted to do all of the Netherlands, and I tried a small area. I'll show you the data of that in a second. Works great. It just does it all for you quite quickly. And now we're kind of at the stage where we have all the data in, you can play around with it. It really links to all the open source different projects. Now I just want to make it faster and a little easier to use, because especially if you work with all the different data types, the learning curve is a little bit steep, I would say, sometimes with all the GDAL and PDAL and all the combinations, as I've experienced myself over the last few years. So how do you make it simpler for people to use all this? So we kind of started making the ingestion simpler. So here is my S3 bucket with all my data. Here's the S3 bucket where I want my array to be, and just go and ingest it all. Doesn't matter how many files there are. You just have to say, okay, these are all less files, so I want point clouds, for instance. That's kind of what we're working on, and then also make it interactively visual, so you can track what's going on. And I just had to mention this. Of course, we're doing vector search as well, because we're an array database, so it fits really well, because vectors are pretty much arrays. So we're now at the point where when you ingest your data, you can ingest your embeddings at the same time. So that's still in development, but there's some use cases that are already quite cool and working well. And I wanted to end with a few visualizations. This is Bristol. Just going to go find my house here in Clifton. And this is kind of this website. You can just play around it yourself. the controls are there. This is also streaming directly from a TileDB Cloud array on S3. Well, this is a movie, so this isn't, but it does when you go to the website. And you can play around with it. There's different ways of controlling it. And especially here you can see it's not going to load all your data at once. These are really prototypes where we have different levels of details. So if you zoom in, it will go and load from a more dense array. And the last one is that this is really, nobody has seen this yet. We're working on how do you combine everything together, really. So this has a sentinel image. You can see a point cloud, still working on it, on the visuals. And then there's also 3D tiles. They also link into that from a different data source. And just playing around and getting the UI right, and especially loading all that different types of data all together in the right projection, which is kind of the interesting part of this. So that's want to end here. This is what we're doing. We're trying to make it easier to combine and mix all the data together, use the tools you already use, and view it all in a single viewer. Try it out for free. And come talk to me if you want, because there's some really cool things I'm going to be working on over the next months, especially with universities. So come talk to me if you're interested. And here's the slides again and my info. Thank you.
Thank you very much for this impressive presentation. Do we have some questions? Questions? We have time for questions. Okay, Jess in the background.
Where's the best place for me to start? With the cloud one or with the local one?
It depends. If you already use GDAL and PDAL and you know how to install the packages, start with open source. If you don't, if you struggle with the installation, go to TileDB Cloud to me, and because it's already there, you don't have to take that difficult step.
Great, thank you.
Okay, more questions? Yeah, we are a little bit over time, but no problem. So then, thank you very much again, Margriet.
Cool.
And